Hi, thanks for tuning in to this installment of the Happy Lecture Series on YouTube. My name's Joseph Slote. I'm a fourth-year PhD student at Caltech, and I'm excited today to talk about some recent work of myself and my collaborators, Lars Becker, Klein, Sasha Volberg, and Haonan Zhang, on a dimension-free version of a very classical inequality known as Remez inequality. This term in the second line, norm designs, is a natural object that appears from this dimension-free Remez inequality. We'll get to it at the very end. But for now, I'd like to just develop Remez inequalities in general. So let's recall the original one. We have a univariate polynomial of bounded degree d, and let's say we want to know its supremum over some interval, j. Suppose further that we only know the value of f over some small Lebesgue measurable subset E. Well, the classical Remez inequality says that the supremum of f over all of j is bounded by some constant times the supremum of f over E. Moreover, that constant has to do with the ratio of the measure of the whole interval j and the measure of this small subset E. It's natural that as E gets smaller and we have less and less information about j, that the constant of approximation should get worse. And I'll just mention that throughout this talk, we'll have this notation, norm of f with respect to some domain x just means the supremum norm. Now, you can ask for multidimensional versions of this Remez inequality, by which I mean you have some function that still has bounded degree, but now has, let's say, n variate. And there are generalizations of this kind. A notable one is by Brudny and Gansberg in 1973. They are interested in convex domains J. But one thing you'll notice from the literature is that all of these results have strong dependence on dimension n, by which I mean the constant, which here is 4 times the ratio of the measures to the d, that also includes strong dependence on the dimension n. And in particular, it's exponential for Brudny and Gansberg. Moreover, that dependence is actually necessary. So here's a quick example to illustrate why. Consider f, which is just 1 minus the sum of squares of the coordinates. So you can think of it as a little hill that is maximum where x is 0 and it decays quadratically. So in particular, if we let our domain j be just the unit ball, then we can ask for an inequality of this kind. And here's an example test set E where things kind of go wrong. So let's set E to be some thin shell around the boundary of the ball. So E is just all of those points with moderately large L2 norm, or equivalently, all of those points for which f of x is less than or equal to epsilon. Well, for all n, of course, the supremum of f over the whole domain is 1, but the supremum of f over E is epsilon. And yet, as n goes to infinity, the ratio of these two measures goes to 1. So if you want an inequality like the kind on the previous slide, you have to involve the quantity n. So that's kind of a disappointment, especially if you're interested in dimension-free versions of a Remez inequality, as we are for some applications, which I'll describe in a second. But you know, the one thing to note here is that while there are counterexamples, there are certain bad test sets E that do require dimension-dependent constant. It doesn't mean that they're all bad. So it could still be that there's a dimension-free Remez-type inequality for certain EJ pairs. And it's these pairs that we study in our work. So here's the arXiv link. It's a preprint as of now. We have several statements, but probably the most closely connected to the current discussion is the following. So our domain J will be the solid cube, so 0, 0, 1, just a Cartesian product of closed interval 0, 1. And our test set E will be the n-fold product of this grid. So there are d+1 points, red points here, and it's the Cartesian product of this, or a little more formally, our E here and our J. We prove the following. So for any degree D polynomial on this domain, the supremum is bounded by a constant independent of dimension n times the supremum of f over this sparse grid g sub d to the n. So some just immediate things to point out. It is dimension free. And also it's discrete. So E has measure 0, and in fact, E is finite for us. This is the first Remez estimate with both of these properties as far as we know. And there have been some arguably dimension-free Remez inequalities in the past. They're very special though. So this is not, it's not like we had both of these things in full generality alone, and this was the first to combine them. It's we're still kind of working out the way in which this result relates to existing work. Okay. So another thing to say is that our result works for other pairs EJ as well, and important for an application, which I'll mention in just a sec, is roots of unity and the polytorus for complex valued polynomials. So here's the domain. E again is our set of red points, and J is the torus. So a little more formally, our omega sub k will always be kth roots of unity. We're interested in the Cartesian product of that as a test set for the full domain, the polytorus. And we proved that for any polynomial of degree D, we have the same thing as before, essentially. So here's with an explicit constant, the supremum of f over the whole polytorus is bounded by something like log k to the d times the supremum over this sparse grid of points. And k here is the individual degree of f. So what I mean by that is treat f, for each input coordinate I, treat f as a univariate polynomial just in xi or zi, and ask what is the degree in zi. K is the maximum over all I of this number. And it's of course never more than d. This becomes important in later, just to make that distinction. So let me explain why dimension freeness of these Remez inequalities were so interesting to us. We have been trying for a while to establish Bone and Bust-Hill inequalities for cyclic groups of arbitrary order. So the original Bone and Bust-Hill inequality is a Fourier analytic inequality. You consider a polynomial from the polytorus of bounded degree, and it turns out that you can control the little LP norm of the Fourier coefficients of f. In particular, p is 2 times the degree over the degree plus 1. You can control this in a dimension-free way by the supremum of f over the whole domain. And this is related to Littlewood's 4/3 inequality. It's a generalization of it. And it has a very long history in harmonic analysis. Much more recently, a version of this has been proved for the hypercube, or equivalently for cyclic group of order 2. So you have a degree D polynomial again, but now it's just on the domain +1 - 1 to the n, which is exactly the multiplicative representation of cyclic group of order 2. And we have, really the same comparison, same estimate. And the torus, the polytorus is kind of like taking kth roots of unity and then sending k to infinity. And it's very natural to ask for this inequality for functions on cyclic groups of order that's intermediate between 2 and infinity. And it turns out that the proof technique, the kind of recipe that worked to prove both the original Bowen and Blust-Hill inequality and this much more recent inequality for the hypercube, that recipe does not work for these intermediate values of k. And this has to do with the lack of a maximum principle, essentially, for cyclic group domains. And there are now a couple ways to prove this. But if we had a Remez inequality like the kind I just mentioned, we get it very, very quickly, just like this. So we have a function from n-fold product of kth order cyclic groups. We consider its Fourier transform, and we just imagine it as a polynomial over the polytorus instead. So we apply the Bowen and Blust-Hill inequality, and we get some comparison that's dimension-free. And then now, from this dimension-free Remez inequality that's proved in this work, we can estimate the supremum of f over the whole polytorus in a dimension-free way by the supremum of f just over the domain of interest, or the test set, omega sub k to the n. Now, one other thing to mention, this entire story about Bowen and Blust-Hill inequalities for polynomials on discrete domains. Part of the interest of this is motivated by a recent work of Eskenazi-Sivanishvili on getting sample-efficient learning algorithms for low-degree polynomials. And it turns out that the dimension freeness of the Bowen and Blust-Hill inequality is the key thing that enables efficient learning algorithms. So there's a lot of history to this stuff, but also much more recent, much more applied aspects as well. So that's some motivation. For the rest of the time, I'd like to discuss how one proves such a thing, and then also introduce this idea of norm designs that we hope is a natural object that could be of greater interest. So let's talk about the proof. Recall that the thing we want to prove, and we'll do the cyclic group version of the theorem. So we have some function on the polytorus. It's a polynomial. It has bounded degree, and we want to control the supremum of f over the whole domain by the supremum of f over these discrete points arrayed about the circle. So in order to get an idea of how to do this, let's just consider the one-dimensional version to start. So here's just a formulation of a one-dimensional interpolation idea. So because we're in one dimension, the degree of the polynomial is the individual degree, so we'll use k. So fix a degree k and consider a polynomial f with degree less than k. Then there exists a function from kth roots of unity to the complex numbers such that for any z in C, for any complex z, A depends on z here. So you can write f of z, so f evaluated at any point on the circle, as the complex combination of some linear combination with complex coefficients of f evaluated only at our test points. And moreover, you can bound the little L1 norm of these coefficients A of omega. So what does this have to do with Remez inequality? Well, we can make the following observation. I'll talk about the proof in a second. So we can make the following observation. With z star a maximizer of the modulus of f, we have the supremum norm of f over the polytorus, just over the Single univariate torus is exactly the modulus of f of z star. And we know that we can write f of z star as this linear combination of f evaluated at our special points in omega k. So then we just take Holder and we have the comparison we want. Okay, so let me just now back up and talk about how this thing is proved. So essentially, I mean, if you look up or recall the formula for Lagrange interpolation, that's just what is written here. To see it a little more slowly, we can say, okay, well, we want this to hold for any polynomial f. So it suffices to require it for all of the monomials. So that here exactly is this requirement for z to the j for all j between 0 and k minus 1. This holds. And this is essentially a constraint system. And if you write it all down, you'll see that it's actually, you get some matrix, and you can recognize this as a Vandermonde system. And so inverting the Vandermonde matrix exactly gets you this estimate and gets you your A of omegas. Okay. So that's 1D interpolation. It gives us kind of maybe a direction to do this argument, and it works already in one dimension. So let's try to reuse this 1D interpolation to handle all the dimensions. So let's note that it does tensorize if we repeat it coordinate wise, and we get something that looks like this. So now f is n-variate. F is being evaluated on this grid of points in each coordinate. So we have to sum over omega 1 through omega n. And we get this big product of coefficients governing f for that point in n-variate space. And with this, we do get an inequality. So it yields the supremum of f is at most big O of log k. Aha, but it's to the n times the supremum of f over a grid. And this exponential dependence on n is not what we wanted. But if you think about it, we'd never use that f was total degree d. So we did use already that it has individual degree k, but somehow tensorization, just repeating this argument coordinate-wise, misses the fact that f is bounded degree in total. So here's maybe the first idea of this argument. If we squint, this first expression here, this big sum, looks a little bit like, well, if we forget that these a sub j's are complex valued, it's kind of like, well, okay, it's integrating with respect to n variables, which is kind of like taking the expectation over n many independent random variables, where these a sub j's is like a product measure. And when we think about taking expectation with respect to n independent random variables, we can ask, how sensitive is f to correlation among these independent random variables? And if you've ever worked in the topic of pseudo-randomness in theoretical computer science, you know that d-wise independent distributions fool degree d polynomials. So this means you can replace fully product distribution on n variables with a different distribution that is not a product distribution, but on any size d marginal, on any marginal of d many random variables, as long as it looks like a product distribution on these small pieces, then the integral of f with respect to the true product distribution, or the integral of f with respect to this modified distribution, will be the same. And so that's kind of the thrust of this idea, is interpret this interpolation expression as probabilistically as integrating with respect to some independent random variables, and then correlate them to try to gain in accuracy. So we don't literally replace this independent distribution, product distribution, with a d-wise independent one, but morally, I think that's the the key idea. So to that end, let's do a probabilistic interpretation of the result that I just mentioned, just this 1D interpolation. So everything is just as it was before. And now we're going to have some underlying random variable t. T will allow us to standardize, these A of omegas are going to be different for each coordinate, but this underlying random variable will be the same for each coordinate and kind of allow us to standardize these random variables. So t is just going to be uniformly drawn from the interval 0 to c. And we have that there are two functions from, they will be eventually functions of t, so r from the same interval, but now just into 1i minus 1 minus I, and w from the same interval to kth roots of unity, such that for any polynomial with bounded degree, we have the following. Okay, sorry, that degree should be less than k. We have f of z is equal to c times some constant c times the expectation over our underlying random variable of the product of these two things. Now this is really just a rewriting of what happened on the last slide. The construction is a bit technical. It's not too hard, but the idea is that t is like a timeline, and as the time moves forward, r and t conspire together to make sure that f is evaluated on each omega for an amount of time commensurate with the magnitude of A of omega, and then is angled correctly, which is enabled by this R of t. So maybe to give a slightly, still a cartoon, but slightly more concrete idea, let's consider k as 3 and put omega to be the first root of unity. And then let's just pretend that f of z, all of our coefficients a are positive real. So the function r won't be involved in this example, but just assume we have that f is, z is such that f of z equals this linear combination. Then what we can do is consider the following. Okay, so c is some constant, but let w of t be this function. It's a simple function, and it will be equal to omega to the 0 on an interval of size 1/8, or c over 8, and then omega for size 2 over 8, and then omega squared for size 5 over 8. So you'll note that the L1 of A is 8, which is why we're doing this. And if we set it up like this, then we see that the integral over t of f of w of t is exactly 1 over c times f of z. So this is what I meant by the r's and w's conspire. If the a's were complex, you would have to rotate them as the time continued in order to make sure they're angled correctly. But that's the general idea of this 1D interpolation. So nothing happened. We just rewrote the earlier interpolation in a probabilistic form. And again, we can do naive n-dimensional interpolation with the expectation values this time. So pick z a maximizer of the modulus of f. And we see this expression here. Again, nothing's changed. We can conclude the same thing as before. Disappointingly, we have exponential dependence on dimension. But now if we look at this, we have T1 through Tn is the underlying space that we're integrating over. And we could instead now correlate T1 through Tn. So let me explain. So the fix will be, instead of using IID T1 through Tn, uniformly drawn from the interval 0 to c, to evaluate this expression, the product of the r's times f, which receives as input this vector of w1 of t1, w2 of t2, etc. We'll only consider m many t1 through tm's IID in the same way. And m here, imagine it is much smaller than n. M is like d, or order of d. And we'll use these to, we'll only have, because we only have m many t's now, that means we have to distribute to all of the r's and w's some copied versions. So it could be like w1, w2 both receive t1, for instance. So the choice of how the t's are associated with the w's will also be made randomly with respect to a uniformly sampled random map from the integers 1 through n to the integers 1 through m. And that gives us the following two random variables: r, big R, which is the product of little r applied to each of the tj's. So there's only m of them instead of n of them above. And then w, which is this vector where we still have w1 through wn, and each of them get some random variable t, but that specific random variable they get is the number 1 through m associated with that coordinate. So they get t sub p of j, for example. And now with these random variables named, instead of examining this first expectation where we did it with respect to n IID random variables, instead we'll examine this expectation here, where now this r is only a product of m many things, and this f takes as input this vector, which has these correlated t's. So it turns out that when you consider this correlated version, you get something that's very nice. So you get f of z is equal to c now only to the m times the expectation of these correlated random variables, plus some error term, p of 1 over m. So let me say that with a little bit more language. This is the key lemma in our argument. So we're given an f and a point on the polytorus z. There's some polynomial. So the error term is a polynomial, such that for any positive integer m, we have these dependent random variables r and w, such that we get this expression. We get this expression here. And one very surprising thing is that the error term, the error polynomial p, has a lot of structure. So it's polynomial, its degree is bounded. Its degree is less than d, and also it has no constant term. So, you know, usually we're accustomed to seeing error terms that are just small, and that's as much as we can hope for. But here we actually have a lot of control over p, and this will allow us to eventually completely remove p. So, you know, if you know that p has a zero constant term, you might be tempted to adjust m so that we're looking at p of 0. But if we send m to infinity, which is what would be required, then you also get c to the infinity, which is no good. So we'll remove the error in a different way, but that's for later. For now, I want to give some idea as to why this expression is true. And in order to do that, it suffices to argue this fact for a single monomial. So I want to claim that z to the alpha, and alpha here is a multi-index specifying the degree on each coordinate, that it's equal to the same thing that we saw before. So z to the alpha becomes w to the alpha, essentially. And equivalently, here I am just rearranging things, where we'll be splitting up this expectation. So it's just nice to see it like this. So e to the r times w to the alpha is this expression here. And just a reminder about notation, z to the alpha is literally that. Alpha is the multi-index. So the main idea will be to condition on the choice of this function, this associator function. And we say that P, so let's study what P does a little bit. So we say P induces a partition S of the supportive alpha in a natural way. So the supportive alpha is just those indices for which alpha is non-zero. Those are the coordinates that participate in the monomial. We'll say P induces a partition S if S is exactly the preimage of P intersected with the supportive alpha. So you think of this big list of coordinates 1 through n. Some of them are participating in the supportive alpha, and then these are further grouped according to P. These groupings are a partition of the supportive alpha, and that's what and these groupings are the partition that P induces. So just very quick example, so let the supportive alpha be this, and let P be this map here. Then we say P induces this S here. You'll see 1 and 3 are grouped together because P of 1 and P of 3 are identical, and P of 4 is something else. Moreover, 2 is not present because 2 is not in the supportive alpha. And then just tiny more notation, P of this tail arrow to S means P induces S. Okay, so recall our goal. We want to show that this holds, and we'll do that by looking at what happens when P induces certain partitions. So there's a particular partition where we can say things very explicitly. So S star for us will be the singleton partition, where each coordinate in the supportive alpha comes as its own set. And when this is true, we can look at our R and our W to the alpha, and okay, R always is this is just for reference, but W to the alpha becomes Wj times T of P of J to the alpha J. And the important point is that these P of J's, for every J in the supportive alpha, this P of J is distinct. So that means W as a random variable is W to the alpha as a random variable is the product of a number of independent random variables equal to the support. And that's critical. So if we look at the conditional expectation of R of W to the alpha, this S should be S star. So conditioned on this very special partition, the singleton partition, we see that the expectation of this product, I've just rewritten R times W to the alpha, it splits because of that independence. So this left term here, I've pulled the expectation inside. We're iterating over all of the J in the supportive alpha, and we have R of T to the P of J. So I'm just associating the T's living in the R's and the T's living in the W's. And because of that independence, we get that term here. And then left over, there's just a bunch of R of T sub L's for those L's that are not participating in the support of alpha. And then from that independence, it's essentially just it's that 1D interpolation again. So we get exactly the monomials we wanted up to some constant factor. Together equals c to the minus m times e to the alpha. So comparing this expression here with the goal, we essentially have the first term. So it's c to the minus m times a sum. We have the first term all set. Of course, it's conditional. It's conditional expectation. Now let's consider when P induces some other S that's not this good singleton partition. Well, it's hard to say much, but we can say this. So the conditional expectation is some c to the minus m times stuff. And this stuff depends only on the partition. So in particular, it doesn't directly depend on our choice of m. And it turns out that that's enough. So because of the following elegant expression, it turns out that the probability that that P induces S, so we're doing conditional expectation, we need to know the probability that these events happen, actually has a very nice form. I mean, this is just simple combinatorics. So it's some fraction where the numerator is m copied the size of S many times, divided by m to the size of the support of alpha. So if you think about expanding this all out and then viewing it as a polynomial in 1 over m, you'll see that when the size of S is equal to the size of the support of alpha, which by the way is equivalent to S being S star, then there's just as many S's upstairs as there are downstairs. And we're left with a constant term. Sorry, there's just as many M's upstairs as there are downstairs, and we're left with a constant term 1. On the other hand, when S is equal to anything else, there are more M's downstairs than upstairs, and there's no constant term. So let me write that. So when the size of S is equal to the size of the support of alpha, that is, when S is equal to S star, we can write it as 1 plus some polynomial in 1 over m, where this polynomial has no constant term. And otherwise, when the size of S is smaller than the size of the support of alpha, we can just write it as this polynomial, again, of 1 over m with no constant term. So in here, and the other thing is that these, because m, because the size of S is always less than the degree of the function, the degree of these q's are also less than d, and they have no constant term. And so with that said, we now can do standard conditional expectation rewriting of the expectation we care about. So this first summand here is the case that P induces S star. And so I have c to the minus m times z to the alpha, that's the conditional expectation, times the probability that it occurred. That's exactly 1 plus this q thing that we just discussed. Okay, now what about the case where P induces something else? Well, we still have c to the minus m, and then it's some stuff times, again, this q polynomial, and there's no, and really importantly, there's no constant term here. So when we rearrange and multiply through by z to the alpha, we get this expression. And P here I've just set equal to what it needs to be, but the point is that P has no constant term and has degree bounded by d. So that has proved our goal, and we have proved this proposition, interpolation with error. Now the remaining thing is to remove the error, and we'll do this by considering a convex combination of evaluations here for m equals 1, 2 through d. So we have this, and we know this is true for any positive integer m. So similarly to that Vandermonde argument earlier, one can show that there are some b1 through bd such that for any polynomial at all with bounded degree and no constant term, you have the following 3 things. You have that the combination of p evaluated at 1 over m with these coefficients is 0. You have that the sum b sub m is 1. And then you also have this bound on the infinity norm of the b's. Taken together, we can write f of z as the sum over bm of f of z, and that's just because the sums of the bm's are 1. But then we for each of these m's, we can rewrite f of z with this interpolation with error form here. And because of this fact above, any polynomial with degree p less than d vanishing, any polynomial in 1 over m vanishing, we see that these error terms p come together and disappear, and we're just left with this formula. and that is bounded as follows. And this is because, so okay, maybe a couple things to mention here. The definition of the R and W, it actually does depend on M, just because that's the number of underlying random variables T involved. But an upper bound for the expectation is always going to be the supremum of F over our grid. Why is that? Because remember that R takes values 1i minus 1 minus I, so its magnitude is always 1. And then no matter how many m's there are, F of W is just being it's just being evaluated in that grid. So we have this bound by the supremum of F over omega sub k to the n times some constants, and without much work, one can bound those constants, and we have our proof. So that, as I said before, this now enables an extremely fast proof of these Bonin-Blasill inequalities and has some applications to learning. I want to also propose a new object that we like to call norm designs. So recall there are these things called designs that show up in several places in approximation theory. So if we have some degree D polynomials on some domain X, and then we have Y, just a subset of X, we call Y a D design if for all such polynomials, the integral of F over the whole domain with respect to uniform or Haar measure, I'm being a little sloppy here, is equal to the integral just over this subset. So these are some very special grids of points or other subsets for which any degree D polynomial can't tell the difference. It can't detect that it's being integrated over one or the other. A classic example of this is spherical designs of Delsart, Goethals, and Seidel, 1977. And given the theorem that was just proved, it's reasonable to consider a version of this for norms instead. So here's the definition. Consider X some domain and S some subset of X. And we say S is a D, P norm design if for all polynomials on this domain of bounded degree, the LP norm of F over X is controlled in a dimension-free way by the LP norm of F over this subset S. So in particular, what we just showed, that when X is the polytorus, we've proved that omega sub D to the n is a D infinity norm design. Now, just from essentially Plancherel, it's immediate that omega sub D to the n is also a D2 norm design. But it turns out, and this is in the paper, it turns out you can prove without too much work that actually omega sub D to the n is a DP norm design for any P in between 1 and infinity. So I think the idea is that these norm designs are naturally related to D designs more generally, and it's really the sky's the limit with either applications of these objects and also figuring out when is a set S norm design, what spaces admit this, etc. So thank you very much. Here's just some list of some related work, and yeah, I welcome any questions. Thanks.